Alright, so this is video one of developing neural networks from scratch in Python. And this video is about what really a neural network is and how they conceptually kind of work. So before we even really get into the information, we should go over some of the prerequisites. We'll be going over mostly algebra regarding the math, but we'll also talk about some math that has calculus and some linear algebra in it, but we won't really be taking an in-depth look, so that everybody should be okay not knowing those two concepts. But regarding the programming part of this little video course, it'll be done in Python, so any experience in that is good. We'll be going up to the some object-oriented programming in Python. So if you're not really familiar with what that is, or if you haven't programmed in Python yet, but you kind of know what object-oriented programming is, you might want to take a look at some of the resources I've attached. Um, yeah, you might want to take a look at some of those like learning resources before looking at these videos. Um, but most of it should be intuitive, so you can just pay attention and then pick it up as you're watching. Um, and with that out of the way, we can start talking. So, all right, so what is a neural network exactly, right? We'll start off with a loose definition just so we can fall back to it later if we ever need to, but loosely speaking, a neural network is simply a computer's representation or model of intelligence. And what do I mean by intelligence? Like, especially regarding to artificial intelligence, neural networks, and machine learning, right? What is intelligence? So simply put, it is basically the ability for something to process information in such a way that it can make meaningful predictions or get a meaningful outcome out of data that it's never seen before. So like an example of this would be a self-driving car from Tesla. So they train their algorithm on road data, right, that they get from various sources, and then they allow this model to drive on the road, and it's getting new data that it's never seen before. It's probably never been trained on this specific road before, but it can still drive on it, right? And that's the case because the model that Tesla uses can meaningfully interpret old data that's been trained on, and then make outcomes or predictions on where to drive, where to go, what to do in a situation that it's never been before. So that'd be an example of a neural network in action, at least. So, intelligence in our brain, if you look at these two pictures right here on the screen, intelligence in our brain uh, is a result of intelligence in humans, my bad, is a result of our brain, right? And fundamentally speaking, our brain works off of connections between neurons. And to the left right here is a model of a neuron we have. And we don't really care about too many of the specific biological parts of this neuron. We simply care about two parts. We care about these little squiggly lines coming in, and then we care about this big squiggly line going out. And we should start labeling these because that'd be good to do. This right here is called the axon of the neuron. These are called the dendrites of a neuron. And you don't really have to know what the names are, but I'm putting a name to them just because we can right now. And these dendrites are simply inputs. We can think of this neuron as a function, basically, right? And we can think of these dendrites as the input values coming in. So these would be like connections to other neurons. And the inputs would be dependent on whether or not those neurons fire. So we have our inputs into the neuron, and then we have one output of the neuron. So this neuron would take in multiple different inputs and then come out with one big output that it sends to multiple different neurons. Now note, although this is branching off into a bunch of other neurons, all of this is technically still one output. It's sending the same output to many different neurons, right? That's basically what it's doing. Get rid of this. There we go. Alright, these on the other hand, the dendrites, they don't all have to be the same. Because they're dependent on other neurons, these are connections to other neurons, as squiggly lines, because they're dependent on other neurons, they can all be different. So this little strand right here, it could be connected to a neuron that is fired. This one could be connected to one that hasn't fired, and so on and so forth. So the inputs don't have to be the same, but the output is going to be the same because there's only one output going into many different neurons. Now this image to the right, this image right here, is pretty much a bigger model of what we just worked with, right? So what we just worked with, that biological model of a neuron, is pretty much the same as taking a snapshot look at this neuron by itself in this model right here, right? And I can say this because this model, the one with dendrites and axons in it, it includes connections to the previous neurons. Those are what our dendrites are. And a connection leading out of the neuron. So this is what our output would be. And if you look at the model to the right, you can see, let me erase this real quick, that we have a neuron. We have a pseudoneuron. We call these pseudoneurons, which are also known as nodes. We have this node right here. And we have connections from other neurons going into it. And then we have an output leaving it. So these two, what I just drew, the connections going into the neuron and leaving it, that is the same as the model to the left with the dendrites and axons. All right. Now looking at the model to the right with all these different neurons interconnected, we can make some observations really quickly. All right, so there are two main observations we're going to make. So the first one is about how they're kind of grouped, right? How these nodes are grouped. They're kind of grouped in columns, if you can see them. There's a column right here, another column right here, and the third column right here. And when dealing with neural networks, we don't really call these columns. We call these layers. So we have these nodes that are grouped in layers. And there's three different types of layers that you can have in a neural network. You can have an input layer, a hidden layer, and an output layer. You can only have one input layer, and one output layer per neural network. And it should make sense as to why just looking at this visual representation. Regarding hidden layers, you can have any number of hidden layers that you would like in your neural network, right? So you could have 30, 40, 50, 1,000, 10,000, each with like 30 million neurons in them. You could have any number of hidden layers that you would like, but you can only have one input and one output layer. So that's the first observation we're going to make. We categorize and group neurons in a neural network by layers. That's the first observation. The second observation is going to be about the relations and the connections between the neurons. So for example, let's take a look at this neuron right here in the middle. This hidden this hidden layer neuron. So as you can see, it has a connection coming into it from every single neuron in the layer that was behind it. And this is going to be the case for every single neuron in our neural network except for our input neurons, because there's nothing to send into them. They only have stuff coming out of it. And this rule still applies if you check the output layer. So if we take a look at this neuron right here, we can see that it has 4 connections rather than 3 coming into it, each from the hidden layer neuron that corresponds to each connection right here. So the number of connections is dependent on n number of neurons in each layer. So this neuron is dependent on n number of neurons in input. And we have 3 neurons in input, so this guy right here has 3 connections coming into it, as well as these guys as well. And that's the second observation. So every single neuron is interconnected to the neuron in the layer that is behind it. Okay. All right. So now that we've taken a look at some of the properties of the neural network on the big picture, why don't we take a look at some of the properties of these neurons individually? So down here we have a diagram of a random hidden layer neuron. It's no neuron in this layer right here, and we know that because by just looking at the connections that this neuron has, right? We see that there's two connections coming into it, so we already know from the start that there's two neurons in the layer behind it, and there's three connections leaving it, so we already know that there's three neurons in the layer in front of it, and we also know that these three connections leaving it are all going to be the same because they're all the same output value, as we discussed earlier in this image. So we as creators give each of these neurons, sorry, two values. We give them a weight and a bias. Okay? And these two values are what we use when trying to mathematically get our output from our inputs, right? So whenever you're trying to get a desired output with inputs in math, right? What do you use? Use a function, right? All right. So what are some functions that we can just think about at the top of our head? The simplest one that I can think about is the equation for a line, right? So we have y equals mx plus b, and everybody should be familiar with this equation. So we have, we can rewrite this, right? Because we know that our y's are going to be our outputs for the function, our x are going to be the inputs. So we can kind of rewrite this. We can rewrite it as output are equal to m times inputs plus a constant. Because we know that the b is going to be a constant. It's whatever our y-intercept is. So looking at this equation, you kind of see how it'll better fit our needs for machine learning and neural networks, right? Because now we're talking in terms of inputs and outputs instead of y and x. And we have inputs and outputs in our neural network, right? Our outputs is what we're trying to solve for because these are our outputs. This is what we're trying to get. These are our inputs. This is what we're trying to use to get our outputs. That just leaves two unknowns, right? We have our m and our constant. And where do we get these from in our neuron, right? And conveniently enough, we can use our weights and our bias to fill in those values, right? So we now get outputs, or output is equal to the weight times the input plus the bias. Now this equation isn't complete yet, and there's a reason why. Say we had a value of 3 for this for this neuron going in, this 3 for the input, and a value of 4 for this input right here. If the weight applied to the entire neuron, right? So say the weight was 3 for the entire neuron and the bias was 1, right? For the entire neuron. How do we compute our output using this equation? Because we have more than one input, but we're trying to get one output. So how does that work, really, you know? And it only works if you move the weight from applying to the entire neuron to apply to the connections between neurons. So the weight for this is going to be 0.5. The weight for this could be 5. But the bias doesn't change. The bias is constant. It remains the same for the entire neuron. So this bias is 1 for both this connection and this connection. So when we shift from having the weight be applicable to the entire neuron to the connections between the neurons, we can rewrite our equation as outputs is equal to the sum of the weights to the nth value times the inputs to the nth value, not to the nth value of the nth value, sorry, plus the bias for the entire neuron. So this is done. They sum the weights and the inputs for each of these connections respectively, and then they add the bias at the end. So for this scenario, we can just try plugging and chugging it just for this scenario right here. We have an input of 4 up here and a weight of 0.5, right? So we could do 4 times 0.5. And then remember, we have to sum all of these. So then we add that to 3 times 5 because 3 is our input for the other connection and 5 is the weight for that connection. 5. Kind of bad handwriting, but we make do. Alright. This is then added to the bias, which in our case is 1. That's 1. So if we just plug and chug real quick, we'll get 2 plus 15 plus 1. So then we get 18 as the output for this neuron. So we'll get 18 coming out here, 18 coming out here, and 18 coming out here. Alright, so let's go over a couple of things we went over. The weights and biases are two values that we give neurons that allow us to do math that lets us get the outputs we want based on our inputs. If we didn't have those values, what would we be doing with these neural networks? Nothing. We'd just be sending inputs in and then sending a bunch of them out. We'd be sending the same inputs into the network and getting the outputs to be the same. Because you're not doing any math with it, right? The weights are respective to each connection. So this would be W1 for this connection right here. And this would be W2 for this connection right here. The bias is applied to all the connections, so it's a part of the neuron itself, not the connections. So here we are. You only have one bias per neuron, but you can have multiple weights depending on how many connections you have. And remember how we said that the connections are determined by however many nodes are in the layer behind you? We can use that law or rule to determine that the number of weights for a neuron is equal to n number of neurons in the layer before. In layer before. So the number of weights in a neuron is equal to the number of neurons in the layer before of it. Alright. And we also took a look at how we actually do the math. So we basically take the sum. So let me come down here and make it look all clean. So the output is equal to the sum of weights times inputs, in which both weights and inputs are going to be changing, right? Because you have a weight per respective input, so both these are going to be changing. And then let me get rid of this right here. Some space. Let me try equals 18 right here. Okay, so the outputs equals the sum of the weights times the inputs plus the bias. And that is simply the output for one neuron. So this would be the output, say this would be the output for this one. So it'd send an 18 to this guy, and it'd send an 18 to this guy right here. And that's pretty much how you do the some basic math regarding hidden layer neurons. Yep. Alright, so now that we've taken a look at some of the math on an individual microscopic level, we can start applying some of the math that we've learned in our understanding of neural networks by understanding how forward passes work in neural networks. So we'll be using this new neural network I made real quick. It has 2 input neurons, 3 hidden layer neurons, and an output neuron. And we'll be using this and adding numbers to it, and then going from input to output, and determine what our output is going to be using some of the math that we learned earlier. And when we do this, right, it's called propagating through the network, right? And basically, this is what a forward pass is. It's simply just propagating the inputs through the network to get the an expected output. So if we have two input neurons, we'll be sending those values to these three neurons in the middle respectively. So this is going to send one to here, one to here, one to here. And it's going to send, this one's going to send its values to this one, this one, and this one. And these three neurons are going to use this math that we talked about earlier, compute their outputs, send it to the final neuron respectively. And then the final neuron is going to use the same equation and then get the final output. And we can call this final output predicted output. Okay? And that's one forward pass in a network. You just take the input data, you send it through the network, and then you get a predicted output. So this is the best guess that the neural network will receive. So if we were still talking about the meteorology example, if this was temperature and this was humidity, this is the best guess as to whether or not it'll rain that day. It'll be most likely a proportion. So not a proportion, probably a percentage. So the output will probably be a percentage. And the higher the percentage is, the more likely it'll rain or something like that. So this is the best. The predicted output is the is like a good guess the computer has regarding whatever data you sent it. And the guess will get better the more and more you train it, right? And on the topic of training, forward passes are extremely important when training a neural network, right? Because it allows us to use backpropagation to optimize the network. And how does it do this? So after you get the predicted output, right, it compares that to the expected output. Where do we get this expected output from? Well, when you're training the neural network, you have data, okay? You've collected data or you've received data from some source. In that data, to actually implement it into the neural network, you'll need two things. You'll need a correlation. Actually, you'll need one thing then. You'll just need a correlation between data. That's it. So if you have expected input, if you have inputs in that data, you'll also need corresponding outputs for those inputs in that data as well. So you could have 50,000 entries in your temperature and humidity readings, and you'd also need 50,000 entries for whether or not it rained that day, because that's what we're trying to find out. So once it sends it in for day one, let's say it sends it through. This is the data for day one that the data was collected. It'll send the temperature and humidity readings through. It'll predict the output, and at the end, it'll use the residual. And the residual is just equal to the predicted minus expected. So we take the predicted output and subtract it from the expected output. And that value we have, right, is basically a gauge as to how accurate our model is. The bigger the residual, the worse off the model is, right? And the smaller it is, the better off it is, right? So it takes that value and it tries to minimize the distance between it. So it tries to minimize the difference between the predicted output and the expected output by going back and using optimization equations, which we'll be talking about in just a second. So that's pretty much what a forward pass is, right? And now let's get started in actually mathematically modeling a forward pass just so we can see how it looks. So remember how we said earlier that each of these weights and biases have their own respective values per connection, right? Not per neuron. So we can say that this weight is 2, this weight will be 1. Let's change the color. And that's the weight connection between this neuron and this one. And 1 is from this neuron to this neuron. We shouldn't use green, we should use something else. Maybe let's call it galaxy. We'll use tan. Okay, so this could be -1, and this could be let's say 0. Why don't we make it 0? And then those are for, oh, I mean, this kind of looks confusing a little bit. Make that -1. And these connections are between this neuron and these connections are between this neuron. I'm sorry if you couldn't see my cursor earlier. I was using my pen. I don't think you can see it that well. So these weights are for, between this neuron, and this neuron, and this neuron. So use a different color. This one. Let's make these connections about 3 and 2. Okay, so now we have our weights for all the connections. Why don't we give ourselves the biases as well? So we'll make this bias 2. We can make this one 3. We can make this one -2. Let's give ourselves the inputs as well. Let's say, I don't even know how to measure humidity. Let's just say the humidity was 6 or whatever. This input was 6, and this input's gonna be 1. So we have our weights and biases for the input and the hidden layer. Now we need it for this one. So we can make this bias -1. How about this one be 0? This one be 3 as well. And the bias for this big boy is going to be 4. Okay. So now that we have all our values that we just randomly made, why don't we try propagating this to the network? So we're starting off with values of 6 and 1, right? And we're trying to compute the outputs for these 3 neurons respectively. And let's start off with our equation. We have outputs is equal to the sum of inputs times the weights plus bias, right? So why don't we go ahead and do that real quick. So for the top neuron, let's go ahead and do that. So we have 6 times 2. That's between this neuron, this input right here, and this weight. 6 times 2, and then we add. And remember, we're taking a look at this neuron by itself, not this one. So we can get different neurons giving us different input values. Different input neurons giving us different input values. Sorry. So we also have 1 times 1 going into this neuron. So we can add that. 1 times 1. And we only have 2 connections. So we only have 2 weights. And so now we're pretty much done with that. So we just added 2 to it. Equals. I'm kind of writing slanted, but outputs 1. Okay, so that's our output for the first layer. And we can just quickly go ahead and do this. Not the first layer, I'm sorry guys, I'm misspeaking all the time. It's the output for the first neuron. So we have 12 plus 1 plus 2. So we have 15 for this guy right here. So we're sending 15 out. And for our outputs too, we can do the same thing, but let's just do it in our head this time. We have 6 times -1, -6, plus 1 times 0, which is 0. So -6 plus 3, that's going to be a 3. So this output's a 3. I'm circling the outputs, or boxing in the outputs just for you guys. And let's do this one as well. So 6 times -2, -12, plus 2, we have -10. And then we have, 6 times 3, 18, plus 2, so that's 20. 20 plus -2 is 18. There we are. And now that we have these 3 outputs, we can treat them as our inputs for this layer now. So we have our outputs is equal to, we can write predicted output actually, it's the final one. Is equal to, so we have 18 times the 3 on this weight. So 18 times 3 plus 0 times 3 plus -1 times 15. Turned out well, not too big of a number. And then we add the bias of 4 at the end. So why don't we go ahead and do this real quick. So we get 54 plus 0 minus 15, actually is a pretty good number, plus 4 equals 0, sorry. 4 equals predicted output. Okay, so 54 minus 11, so we get 43 equals the predicted output. Now this number would never usually be this high, right? It's only this high because I'm using big numbers like 6, 2, 3, negative 2, 3, 4, right? I'm using these bigger numbers. Usually whenever you're giving the data into the neural network, you want to normalize it. And what I mean by normalize it is you want to set boundaries for the data. So usually it'll be in between the values of 0 and 1. So you'll take all these values and compress them to be values between 0 and 1. And when you do this, you don't lose any of the relationships in the data. So all the relationships in the data stay preserved, but the whole the value, the magnitude of the data kind of drops. So you don't really change anything other than how much computational power it takes to do these calculations, I guess. So a couple of you guys might have questions regarding as to how we know what values to give as the bias and the weight for each of these neurons, right? So how do we know what W1 equals? How do we know what W2 equals? And the thing is, we as the creators of this neural network, we don't tell it what the perfect W1 is supposed to be for this neuron for it to be the best neural network in the world. We don't tell any of it that. The computer will use optimization equations to optimize the weight and bias by itself. It'll use gradient descent and some pretty advanced math, which includes calculus, linear algebra, using partial derivative, everything like that. It'll use some pretty complex math and then go back individually. So say it'll start at the output. It'll go back to each layer before, to each neuron before, and then it'll use math to make the residual, which is basically the output that the model received versus the output it expected. So when you're training it, right, and it takes the input and it sends it to the model, whatever it gets, it'll compare to whatever it was supposed to get, and then it'll try to make that number as small as possible by going back layer by time and adjusting the weights and biases bit by bit, slowly but surely, right? Until it gets until the the equation better fits the model and the residual is lowered. So yeah, that's pretty much how we get the biases and weights to be what they are. We as the creators don't do anything. We let the computer, we initialize them as all zeros or randomize them to initialize it. So there'd be random W1s and B1s, and so there'd be random weights and biases for all the neurons when we initialize it. But as the model starts to train, and as it starts to lower the residual, the weights and biases will slowly shift to whatever value is optimal, depending on whatever you're asking it. And regarding the specifics, we as data scientists don't exactly fully know why the model does what it does. And it's this dilemma that has led to the increase, actually, in popularity of understanding the black box that is neural networks, if that makes sense. Many people are now interested in getting experience in understanding why the neural network does what it does, rather than just making neural networks. So that's something to look out for, because many of these big companies, many of the people that are looking for these high-end neural network creators and developers, they're looking for people that understand fundamentals. They're looking for the people that understand how these networks work from the scratch, which means understanding this math, which means understanding how backpropagation and these optimization equations work, right? And that's basically what we're doing right now. So developing the fundamental is something that we're doing and should always be done when learning a new skill. So that should be everything for video 1. We went over a couple different objectives today. We we learned why we model the brain while making neural networks. We learned how we model them mathematically and conceptually, how they kind of work. Uh, and then we also mentioned optimization and how neural networks adjust weights and biases without the need of extraneous help. So we did a couple things today, and see you guys next video.